Okay, so good morning. Let me continue my uh, lecture on this particular topic of unsupervised learning, and we are discussing about the graphical methods. And there, in the last class, we have seen that how the clustering problem can be mapped to a click finding problem, and in particular, to handle noise, we need to consider the problem as a corrupted click problems, which means some of the edges may be noisy in the graph, and how the graph is formed that we discussed, where every data point is the node or vertex of the graph, and every edge is established by connecting those data points or those nodes whose distance is less than certain threshold. So in this way, you get a graph, and then from the graph, you are trying to find out the clicks. And the problem here is that since there is noise, so some of the clicks will be corrupted in the sense that some extraneous edges may be inserted into the click graph, or some of the edges of the click graph may be deleted. So in that case, this problem states that what is the minimum number of deletion or addition of edges in the graph, considering the same vertex set, that would transform the graph into a click graph. Okay, so that we discussed in the previous class, and in today's lecture, we'll be discussing uh, two methods, and as you see that this problem is NP-hard, so we have to use heuristics and we have to consider an approximation solution. You may not get the optimal solutions with respect to the problem statement what I just mentioned. So these methods, two methods, one method is parallel classification with codes, and cluster affinity search techniques. We'll be discussing under this particular problem. Now, uh, here I should mention once again that these algorithms, these clustering algorithms are very much applied to the field of bioinformatics, handle their data points. They have a large data points, and uh, so these algorithms needs to be considered under that context also. So the parallel classification with codes, what it considers, let me give you the principle before going into the steps. The idea here is very simple. The idea is that if you have, of course, large number of data points, why don't you consider the click finding problem for a small set, for a randomly sampled set, so that you can consider all possible combinations of clicks given a finite number of points. Now, this set has to be very small, otherwise, as you understand, combinatorially, as it is explosive. So if you can restrict this number, since these are all power, that you have to restrict this number in the order of logarithm of the data size. In fact, logarithm of the data size that we'll see uh, when this particular algorithm is designed. And there, what we do that we consider every possible click combinations on that sample set, uh, given the, of course, number of clicks that is specified. That means how many components are there. With respect to that many number of components, you can find out what are the possible configurations of clicks on those on the data points, and then you choose each combination, and then you do something to extend that kind of nascent clicks or prototype clicks to cover all the data points. So basically, you are something like similar to one nearest neighbor classification. When I give you the cluster centers, like in K-means, what we do it, of course, in the context of this kind of graph representation. So we'll see that how it is done. So every other data point is extended to that click, and then since you know already that what is your source click and how it has come to this representation, there you know that what should be the number of edges that you can delete or that you can add with respect to these two representations, and that is the number you get. So you consider all possible combinations, and whichever is the minimum you choose, that is as a result, and that itself gives you a partition in the data space. So let me just go through the computational steps, exactly what is described in this particular algorithm. So you see that as I mentioned that you are randomly sampling a subset. So you consider S prime is a subset of S. And first, let us understand the concept of extension. But then we will again discuss about the algorithm, because there are two stages of subsampling we will see. So what is meant by this extension? How do you do it? As I was explaining, that suppose in the subset S prime, you have the partition, say K partitions. As I mentioned, the K number will be also given. That is also an hyperparameter. So these clusters are given to you. Now you have the larger set S, which is the superset of S prime. That means there are points in S which are not belonging to S prime, and you are computing the inclusion of those points or attaching those points to one of these clusters. So there, what we do that we find the number of edges from that point which is not included in S prime to the cluster, to every partition. You find what are the number of edges. That means the vertices, how many vertices of the cluster Ci is connected to the vertex, say J, okay, and which is not included in S prime. Please note that. So that number, and what you do that you can use that number itself as a strength of its affinity. We call it affinity, but as you see that the probability of connecting to a vertex of a cluster Ci, it also is proportional to the size of the cluster. So if you have more number of vertex in Ci, so naturally this number would be higher. Now, chance is higher. So that's why you should normalize it. You should normalize this measure by the cluster size. And this is your affinity. So given a vertex J, you find out what is the highest affinity, maximum affinity for a cluster, what is being given to you. So you connect it to that cluster. So that is what is meant by extension. Now in actual PCC algorithm, you do two stages of extension. So you just select subset S prime from S, and again S double prime from S minus S prime, right? And first as you see that your and also you consider that now what is the size? You restrict that sampling size of the order of logarithmic n in this fashion. You can see that the S prime size is logarithm of n, log of n. N is the number of data points, and S double prime, its size is of logarithm of n, right? N could be quite large, and so suppose n is say 10 to the power 32, if I say. So S prime would be S double prime would be say 32, and S prime would be say 5. So something like that. So I'm just typically giving some example. So, but no, that many numbers you are sampling, and you understand that S double prime and S prime and S double prime, they are all disjoint. Right? So because S double prime is a subset from S minus S prime, right? So then what you do that you consider the smallest subset S prime, which is of log of n. With respect to my example, that is of 10 to the power 32, say the size here is 5, and for all K partitions, so you have to consider the number of K. Naturally, since you are considering number of partition, it cannot exceed the log of n, huh? Because minimum we are not considering any empty partition once again. So at least every partition should have at least one element. So that is a restriction. That's why K is also restricted in that sense. So first you do all possible partitions. No? So you can consider there are say since there are k partitions and you know that the size is log of n. So every point can be partitioned, can be labeled with one of these k. So that is a combination. So you can have k to the power of log of n kind of combination. So which means suppose in 5 data points, if I have say only 2 partitions, so I can have 2 to the power 5 combinations of partitioning. Each partition will represent me and give me a clique because all of them could be connected. I mean that is what is they are actually representing the clique, right? And then you obtain the extended partition in S through 2 stages of extension. That means first you extend S prime to S double prime. That means you extend the data points of S prime to S double prime to the partition of S prime, and then again because these 2 stages of extension make it more robust. So one stage will give you more some number of edges, etc., and that has an effect. That has some cascading effect is there, and for that the 2 stages are suggested. Why 2 stages, etc.? These are all empirical. And why not single stage? Why not 3 stages? Why not 4 stage? These are all empirical. After doing experimentation, the scientist who has proposed this algorithm, they have considered this is the best. So, so choose the one which has minimum score, that is number of edges required. So now this is the interesting, because if I give you the extended after extension, you get a graph. Right? You get a graph, and so in that graph, you consider those edges which are inserted to those cliques. Now there are cliques and there are edges. By following this principle, what I mentioned earlier, affinity principle, you get the new edges. So you get a new graph, and with respect to these 2 graphs, you find out the number of transformations that you require to convert this graph to a clique graph with respect to the partition from which it has been extended. Right? You have to consider only that clique which is under considerations. For every combination, you choose, you do this, you find out that number and choose that combination which gives you the minimum, and that is the result of this algorithm. So some example, if I tell you, if I just discuss here. So you see that suppose this is the graph after extension, and you consider that there could be, let a partition P with k equal to 2 is 1, 5, 6 and 2, 3, 7, 4, which means I have the clique graph with respect to the P, where as you see 1, 5, 6 will give me the clique in this way, a triangular shape, and 2, 3, 7, 4, you can find that all of them are connected. I can represent in this fashion. So now you see that how the problem here is that what is the number of edges that is required to be deleted or inserted so that this graph is transformed into this one. So that is the problem. So you can examine that which of the edges are present here and here. So keep those edges, and which of the edges are present here but not here, you have to delete them. Similarly, which of the edges which are present here and not here, that are to be inserted. So that is what you need to examine and count the number and do this thing. So let me continue with this example. So you can see that with this kind of consideration, so we can find out what are the edges to be added in G and what are the edges to be deleted in G, and then you count out this number. So the score is 10. So this is one possible partition, but you can see that 1 could be replaced by 2, 5 could be replaced by 3, 6 could be replaced by 4, and they could be exchanged and you get another partition. So you have to carry on doing these things for, as I mentioned, that k to the power log of log n or number of partitions, right? Which is essentially, you can see that you can equivalently express as log n to the power log k. And in each iterations, you have order n square operation for extension and score computation. So finally, your total time complexity becomes order n square log n to the power log k. Any question on this part? This algorithm? Okay, so let me continue with the next method. This method is more like a region drawing method. It really does not work on particularly in finding clicks. Rather, it tries to grow regions one by one and try to get the maximal connected components and then extract it, and then again it start doing it. But there is a concept of how these regions can be grown. So this algorithm is called cluster affinity search technique. So someone's microphone is so unmuted. You have to mute it. So here the concept is that it is, as I say, that we are going to define a feature which is close to a cluster C and which are distant from cluster C. That means if I consider C is a set of data points and take any particular point, and we find out any particular, including the point within the cluster also. You can start with a small, you can start with a very, no, I should say, with a reliable data points which should form a cluster, like for example, the nearest neighbors of a pair, or nearest neighboring pair, which means the distance of a pair which is smallest you can choose, and that would be your, say, the seed data points of that cluster. And then you find, with respect to those 2 points, you find out that how many of them are close and how many of them are distant. Distant within the cluster and close outside the cluster. So which are close outside the cluster you include into it, and which are distant within the cluster you exclude them. And you go on doing this thing till you get no point to be declared as close or no point within the cluster to be declared as distant. And then you define that is your one cluster. You consider that is your one cluster. Take out that cluster from the data points, and then you do the same thing in the remaining set, and you go on doing till you all your points are exhausted. So you see that one of the advantage of this method is that you do not require the number of cluster, and that is one great advantage, and that is why it is very popular in, once again, in the bioinformatics area. So I mentioned the definition of closeness to a cluster would be no distance from that data point to a cluster should be less than certain threshold. Now, how this distance to the cluster is measured? Once again, it's a, as you see that it's a point. I is a data point and C is a set of points. So you can choose any kind of heuristic measures. You can consider the average distance. You can consider the minimum distance. You can consider the maximum distance. Whatever is logical, you should do it. That is what is there. Usually, the average distance is used, I think, in this case. So this algorithm, I just what I mentioned, you can find out actually this is what is mentioned. So I'm not going to describe in this way. So please go through these steps, and it is simple enough to say it's a kind of region drawing algorithm. And but every iteration the region is updated. So it grows region one by one. Every iteration a region is updated by finding out the number of points which are outside that region but which are close to it, so including them, and by discarding the points which are within the region but not close to it, that means which are distant, discard them. And when you get a stability, then you take out the cluster. That means no region, no points are declared, new points are declared as close, and no points within the cluster is declared as distant. So one of the interesting part is that this algorithm actually converges in most cases, though there is no theoretical guarantee. It's a kind of heuristics, but in most cases it converges. So the last algorithm, which is, I should say, one of the very popular clustering algorithms in nowadays, and you will find its name in our mostly in clustering literature. It is one of the mostly widely used algorithm because of its some properties. K-means is at one side, and this is another algorithm uh, which takes care of many of the disadvantages of K-means. Now, this algorithm is also actually a graphical method-based algorithm, though explicitly does not represent any graph. So you see that the name of this algorithm is, this acronym is very popular, DBSCAN, and there is a full name, density-based spatial clustering of applications with noise. So first, the paper when it came out in '96, no, that is the name of the paper and name of the algorithm, and everybody calls it in the name of this acronym, DBSCAN. As I mentioned, no explicit computation of distance graph is required, but there is an implicit representation. So of this connectivity and of this graphical implying the graphical representations. So we consider a data point here, and you can see here, suppose a data point is marked red just to highlight that on this data point is going to be tested. And what we are going to do, that we find out defining a particular parameter say epsilon and consider how many data points are within that distance of epsilon, centering at that point. Now, if you find enough point, then we say that this point is a core point, which means it is in a kind of a dense region. So we actually try to grow regions. It is also a region growing algorithm. So once you get a core point, you expand it, and you go on expanding till your all such core points. So if it is not, then this point is not a core point. That's all. That is the first thing. That means if not enough. So there are two parameters. One is epsilon, another is a threshold, which says that whether it is enough or not. So we call this threshold a mean point, mean PNT. So let me just read it as mean point. So that's the threshold. And so if the number of points is within this threshold, you can use equality, greater equality also. So then you call this is a core point, right? Otherwise, this point is not core. Now, once you get a core point, then actually you grow region. So what we do after getting core point, you check its neighborhood points. Again, you find out whether there is any core point. If there is any core point, you go on doing. So in this way, it's a kind of depth first search, as you can understand, or you can use also BFS, like the way you can traverse. And once there is no more point to be expanded, you stop there. Now that may not be your complete region. I mean, it could be a sub part of the region, because then you have to start with another core point. Now, if you find at certain point, core point of one region is merged with another region, so you have to merge them. That means all connected core points should be in the sense of this connectivity. That means a core point would be neighbor. So we call this point is a neighbor. All these points are neighbors. So when core points are neighbors, so all connected core points form a region here. And the points which are not core points but within the region because of connectivity, because they are neighbors to core points, they are called border points. And there would be some points which is neither core and non-neighbor to any core. They are called actually noise points. So these are the three categories. So grow regions of connected core points from a set, a neighbor but not a core point called border point. And as you can see, the advantage is that it forms clusters of arbitrary shape, and you can use efficient search, because it is quite computational intensive. You are finding out the neighbors, and at every point you have to make a search. You have to make a search, and there are efficient spatial data structures to make query on the spatial closeness of the. So region tree or art tree, those are kind of data structures. You can read them if you are interested. So as such, the search should be otherwise linear at every point, but using art tree, you can make it logarithmic, of order logarithmic. A point not reachable from any core point is noisor out here, and I just mentioned. If I show you some visual representations, like Joyashree, she is working on this problem, and she implemented some of the results. So I'll be just showing them. See, if I give you a distribution of data points and you apply this algorithm with some appropriate suitable parameters. So how many parameters are there? Can anybody tell me how many parameters I have just mentioned in this algorithm? Like Yashika, can you tell me the number of parameters I mentioned for DeviScan? I don't see Yashika is there. Hasita? Is Hasita there? Hasita? No. What about Charan? Jatu Charan Sai? Cannot get you also. Shubham? Shubham Kumar Das?
Yes, sir.
Yeah. So tell me, Shubham, how many parameters are there?
There are 2 parameters.
Okay. So what are the implications? What are they? What are those? What do they signify? Can you tell me?
There are 2 parameters, EPS and mean points.
Yes, epsilon and mean point, right?
Mean point.
So epsilon is defining the radius of neighborhood.
Yes, sir. Neighborhood.
Right? Radius
Yes.
of neighborhood. And mean point is defining the
Minimum
criteria
number of points in the.
criteria for declaring a point as a core point.
Yes, sir.
Right? Is it clear?
Yes.
Okay.
Yes.
Great. Thanks. So you see that in DeviScan, you can get visually, we can see that no, it is as per our understanding, this clustering should be okay. There are some distinct gaps between these two groups, and it is being captured. But if I apply k-means, because as I mentioned earlier, the shapes needs to be blob structure, spherical structure, convex structure. That's the kind of assumptions in k-means, and there should be good separability in that way. But the problem is that no, you can see that some of the points, border points, they get misclassified. They get no, in our sense, they are not clustered properly. They go to the different. So there are no some issues here. So that is the advantage of DeviScan. On the other hand, you know that k-means is very simple, and also DeviScan is very computation intensive, where k-means less intensive, but still no, you know that k-means also deal with all the points for computing distance. But DeviScan is an iterative, so that's why it takes a lot of time. So I will also show you some of the results of effect of varying parameters. Now you consider this kind of shape. So these are the shapes which are, for the sake of simplicity, I'm showing it in 2 dimension, but as you understand in higher dimension, it gets more complicated or more complex. So these are the shapes which are very difficult to handle with k-means, as you can understand why it is so. Because no, and also it depends upon our interpretations. How do you define a cluster? For example, you consider this, whether you should consider this as a 2 cluster, or because of this connectivity, whether you consider it as a single cluster. No, that depends upon your context. Similarly, you consider say this point. So that is another issue. So in DeviScan, you do not require also number of clusters. So that is another advantage. In k-means, you have to be given a number of clusters. So if I use different different parameters of DeviScan, as you can see that with respect to this parameter, you get this part as a single. These two are single cluster. No? So I just mentioned earlier. So these are single cluster, and you have already you consider minimum points is 5. So so with respect to this, now these are declared as core points and they are connected, right? So some of them are core points and they are connected because of this. But the problem here is that now if I vary the parameter, so here minimum point is 15. I made it more stringent to declare a core point. So you can see that this cluster gets separated. These groups get separated. Now, whether this is desirable or not, it depends upon the context, as I mentioned. So these are the advantages you have in DBSCAN. You can vary the parameter, and you can get some, depending upon context, you can get your desirable result. Another example is also there. This is another example. So you can see that how the results could vary if you know if you just increase define this kind of criteria. But once the challenge is that how to get these parameters. That is also another challenge in DBSCAN. And there are many works for that. You can read some papers, good papers on that also. So let me then conclude this particular topic, as we have discussed about different techniques of clustering, which falls under this unsupervised learning. One of the major computational problem under this is clustering or grouping. So we have considered semi-parametric approaches like K-means algorithm, or though there is no explicit parameter estimation. But now we have discussed also another extension of K-means under a probabilistic model. By modeling the data set, the probability density function of the data is a mixture of Gaussians, and then identified each components of that mixture as a particular cluster. So in the probabilistic interpretations. So we use expectation maximizations for that method. Then we discussed about hierarchical clustering method, where we build a tree following a bottom-up approach, and as you can see that it uses distance matrix instead of explicit feature representation. That is the advantage. In some cases, no, it is difficult to measure also features, but it is easier to measure the distances among the pairing points. So there also hierarchical clustering becomes more effective or more appropriate. Under the graph-based approaches, we can see that how this problem is mapped to a clique finding problem, whether a clique is a graph with every vertex connected to every other vertex, and a clique graph is that each component should be a clique, then you call it a clique graph. And the problem of clique finding is that your distance graph to be mapped to a clique graph with certain transformation. So what is the minimum number of transformations? That is the corrected clique problem that we discussed. There are methods like PCC and CAST we have considered. And finally, we also discussed about this algorithm, DBSCAN. It's a kind of region growing algorithm for getting the partitions. Though it is not like a region growing algorithm, you get a region and then extract it, and like what you do in CAST, but in DBSCAN it is very different. Regions are grown, but no, regions can be merged once you find that between two regions there is a connectivity. So that part also you have to consider when computing the clustering in DBSCAN, the DBSCAN. So with this, let me stop here. And in fact, today I'm not going to discuss any new topic, though I have some time. You may ask me some question. And also there are certain announcement I did earlier, just to remind you that on next Thursday, and which I suppose is 7th October, you will be having your second quiz. And the syllabus of that quiz is till what we covered, the topics covered after the first quiz, topics of our first quiz, and till today. Next week I will start a new topic, but that won't be in the syllabus. Now, the topics what has been covered, as you can see that we have covered evaluation of hypothesis, and then the Bayesian inference, and then the parametric and non-parametric methods of Bayesian inference, and this topic of unsupervised learning. So any question from your end? Okay, in that case, let us end the session here. And Thank you very much. Bye.